Hello, everyone. Thanks for the invitation and thanks for the great intro. I hope I'm not going to take too much of your precious time before lunch, so I'm going to be quick. So today I want to tell you a little bit about 3 success stories of computer vision. So we've heard quite a bit about reinforcement learning, and as Philip mentioned, it's quite a lot of research going on here. I want to actually show you that the research that we've been investing in for the last couple of years starts to turn into reality. So I'm a chief scientist at Tooploox, where I lead a machine learning team of bright and smart people, machine learning, computer vision, NLP engineers. I'm also an assistant professor at Warsaw Uni of Technology. All right, so yeah, a little bit more about myself, but just a few words. I was a visiting scholar last year at Stanford. I did my PhD in computer vision, machine learning in Switzerland, and I work a little bit in a few of those companies that you see in this slide. All right, so how it all started. So computer vision has started actually over 50 years ago with this tiny little summer project. MIT guys are super ambitious, so they thought they were going to solve computer vision over a summer project, which apparently was not the case. So the idea here was to find a set of algorithms to detect and recognize objects. It turned into a field of research that sparked quite a bit of interesting papers and still hasn't been solved yet. So why is it so difficult? Why is it so tricky to train a machine to understand what's going on in the neighborhood, what's going on around, just using images? So let me give you this example. This is an image of a planet, and if I ask you what do you see there, you probably say a hill, and there is some sort of a crater inside. Now, I give you this picture again, and now probably most of you would tell me that this is a crater and a hill inside. Like, to be honest, it's the same picture. It's just flipped around. The reason why you believe it's a different one is because you assume as humans that sun is above. And clearly it's a quite smart assumption, like we don't have sun shining from below the ground. But machines are not so smart. So for them, this is just a bunch of pixels. This is just an intensity values that are being displayed in a row. However, for many, many years, and this is why we've been fighting with computer vision problems for so long, we tried to approach it from a geometrical point of view. So we tried to kind of encode all this complexity that I just mentioned and just turning around the images and understanding all the priors that we have within our visual system into a bunch of rules, if, conditions, and so on so far. This is the field of computer vision, as we call it, a classical computer vision, but don't confuse it with Greeks. It has nothing to do with Aristoteles or other guys. It's mostly based on geometry. It's mostly based on algebra, on multiplying matrices, and that's why, and light propagation and camera models. But does it always solve your problems? Well, not necessarily. Especially in the cases where you actually need some additional knowledge that we as humans learn through our life. Computer vision needs to have the same sort of approach, or to solve the problems that we solve every day, like detecting objects, classifying them, segmenting the objects that you see around, recognizing what is a tree, what is a car, is it close to us, is it far from us. If I go close to the tree, is there any likelihood the branch will hit me? All of those sort of things are connected to the visual stimuli that we have, but machines don't reason the same way, so they don't know if everything as we do. And that's where machine learning comes in help, and that's why we have such a great, a bunch of advancements in computer vision coming from machine learning community. And that's why actually machine learning also uses computer vision and visual stimuli as one of the best applications and best battlefields for testing if it works. So instead of creating complex cognitive models that we used to do before, now we have data. And why is this so, why is it moving on so quickly in the last years? Mainly because of three reasons. First, the abundance of data that is digitalized in a format that machine learning algorithms can actually digest. The resources, we have a lot of GPUs that we can optimize our algorithms for, and we have models like neural networks, convnets, recurrent neural networks, GANs, and all that. And why is it interesting for machine learning researchers to actually look at vision? Because it's one of the most complex cognition tasks. So more than 2/3 of our brain is actually every second involved in analyzing the visual stimuli around us. It doesn't need to be always reasoning. It can be also linked to like movement, touching, and stuff like that. But our brain is basically full of neurons that are constantly reacting to the stimuli that we get from our eyes. And also a recent study found that people remember 20% more things if they actually saw it with respect to just audio signals that they may have heard. And so with all that introduction, now the funny part, like we have done so much research. Now let's move it into production. Like this is something that all of us developers want to see in practice, right? Like research is cool. We can play Dota for hours and hours, but at the end of the day, we want to have something that works in reality. So this is exactly the moment where computer vision gets commoditized. And this is the moment where computer vision reaches maturity. These are the models like over here you have a YOLO 9000, you have object detection, object recognition that is exceeding the capabilities of humans. It's super fast. You can also find models that are actually translating what images in summer look in the winter, just purely from machine learning point of view. You can also start to see the results where we can reason about what's going on in the photo or in the picture, answering the relational questions using computer vision. So this is the point where we start to see that computer vision can actually be useful. Finally, somewhere you can apply it in production. So this talk today is about things that work. Basically, like a washing machine, you come back home and you just turn it on. You don't care about what sort of CPU or GPU or whatever runs on it. You just want to make it work. And this is the topic of my talk today. These are 3 success stories that, together with our team at Tooploox and also at Warsaw Uni of Technology, we have been developing, we've been working on that, and I can, tell you that they actually work. So first one is visual style search. This is an engine for looking, so analyzing images and looking for similar images, both in terms of visual similarity, but also the stylistic similarity. So not only just the solution that the Google Images gives you, but also some sort of a feeling of what fits together in your room or in your wardrobe. So what is the problem? Well, let's say that you have an image of a room of your friend when you enter this room, and you want to take a picture and find something that looks similar. You want to have it in your home, but you don't want to have exactly the same thing. You just want to have something that is similar in terms of style and in terms of visual similarity. So you take that, you add a fluffy, because you want to have something that is a little bit more fluffy, and you get a bunch of results. This is basically the problem that we're trying to solve. And as you see here, there are 2 components. First of them is visual, so you have image, and the second one is textual. Now, how do you combine them, and how do you actually make some reasoning out of it when it comes to the similarity in terms of style? That's what the first success story of computer vision is. So these are the results that you would get if you upload this image into Google. These are the images that Google would retrieve. Obviously, that's not exactly what you were looking for, but that's fine. This is where our style search engine comes in help. So we have an image, and we add, again, the fluffy word, and we get a bunch of results that are a little bit closer to what we wanted to see in terms of similarity. Obviously, we need some data. So we looked at the best furniture company in the world, IKEA. Woo. They have like 2,200 images on their website with over 300 descriptions of the rooms, which is great. Like you have a lot of nice data that you can play with, both in textual and visual space. And this is what we started to play with first. We started to detect objects. So this is an output of YOLO, the previously mentioned object detection system that allows you to basically get where the objects are and classify them quite nicely. The magic sauce within YOLO is that it runs at once, so that's where the name comes from. It's you only look once, YOLO. The idea is you have a network that actually at the same times gives you the bounding boxes, so the places where the objects are, the class probabilities of those objects. And this is how it's trained. It's optimized for this objective function or objective loss, and that's why it's so fast. Okay, so we detected our objects. We have a bunch of them. Now we look for visual similarities. This is the first part. You see here that we retrieved, using some sort of visual similarity, a bunch of similar chairs, watches, and sofas. What do we define as a visual similarity? To make things simple, we actually extract the penultimate layer of quite famous ResNet model. This is a model that has been trained before on ImageNet, a big data set of images with the proper labels. And the method to actually extract those activations using Python is quite compact, and you can do it by yourself as well. The last part, include top equals to false, means that we actually don't take the classification results, we take the activation functions, which can be a fairly complex representations of visuals. And this is what we get when we actually map it into 2D space. So this is a result of a Tsny operation, so a dimensionality reduction technique that is often applied when it comes to multidimensional spaces. And as you see, the objects that look similar are actually clustered together. So you see the white wardrobes or something like that close to each other. You have white chairs and chairs in general also close to each other. So great, we have the visual part solved. Now let's look at the textual part. We trained our model with Word2Vec. That's a method to basically embed a lot of text into a multi-dimensional space using context. So we had those descriptions of rooms. We knew where the chairs were showing up in this similar context, and we mapped it again on a 2D space using Tsny. We actually labeled, so the colors correspond to the types of the rooms, or to basically room types that the objects came from. And the red one is, I think, a room, while the orange one is coming from the bathroom, right? So it's just purely on the textual level. So we actually didn't take any images into account, but you have images displayed just to see that this stuff works. Cool. So let's put it together. We have visual part. This is the image that we input into our engine, and you have a bunch of objects. You retrieve images that are similar. Now you add the textual query, so you add this fluffy part, which gives you this additional context from the textual information, and then you blend it together. By blending, you basically mean like combining those two models together and just having it in one place. This works fairly well. It's implemented. It's actually run in real time on our mobile device, which was great. The only problem was that it was not end-to-end. So from a machine learning perspective, it's not fun to have something that is just stick together or just glued together from a bunch of modules, because you cannot optimize for something that you really want to optimize for end-to-end. So you don't want to have something that is just glued together. You want to have something that is a big system. And this is why we looked at end-to-end training. We actually used an approach for visual captioning. This is an application that allows you to input an image, and that gets as an output a description of what's going on in the image. So in this case, it's just a description of a steamship at the dock. Now, this is the approach from 2014, where they looked at the images and the text that describes the images, and they map it to a multimodal space, and then try to reconstruct this textual description from this multimodal space. We don't care that much about reconstructing, so we just look at the first part, and we use this approach to model our multimodal space, textual and visual, when it comes to the similarity. And this is what we got. So we had a bunch of tests, and obviously these are the best results that we got, so there are awards for sure. This is the input of an image of a table. You add glass, and you get a bunch of tables that are sort of glassy. They have some glass component in them. Similar for the chair, when you add a white table textual description to your chair, you would get a bunch of chairs or a bunch of tables, and actually the tables have wheels, which you might think it's a coincidence, but it's not. The chair itself also had wheels, so that's why it was found from the visual search similarity. All right, cool, and this is how it actually works in real life. So this is this, success story part where we actually have a running mobile app that you can use to take a picture of your neighbor or your room, and you can then, retrieve visually similar images. Okay, so this is it. The second story is about particle collisions at CERN. As you might have heard of, it's a big laboratory for nuclear physics located in Switzerland. We have research projects with them at Warsaw Uni. And there is an adversarial training part, which I think it's quite important for you to follow those few slides. It's basically the quote of Jan LeCun, one of the biggest leaders of the field of deep learning, and he said that adversarial training is the coolest thing since sliced bread. Kind of agree with that, but not entirely. I think sliced bread might be still a little bit better, but it's pretty cool. So what are GANs, or generative adversarial networks, that Jan LeCun mentioned? These are quite interesting concepts of two networks stick together. One is trying to counterfeit the other, so one is trying to deceive the other, and the other is trying to find out what's the true or versus false, or what's the real or false data. So in this case, you have a Leo DiCaprio who's trying to counterfeit a bunch of checks. This is your generator network. We basically try to generate as many counterfeits as possible. And you have a discriminator, in this case Tom Hanks, who's looking at the images of the real checks and those that are manufactured by Leonardo DiCaprio. And now the generator itself tries to get better and better at counterfeiting, while the discriminator tries to get better and better at discriminating between the true and false. So this, in principle, looks like that when it comes to maths. It's actually min-max game coming from game theory, where you have you can find a Nash equilibrium of those two elements. One is linked to generator, the other one is linked to discriminator, and you have basically this kind of a game where you stop the generator, you train the discriminator, then you stop the discriminator training, and you train the generator, and so on and so forth, and you just iterate between them. And this is what you get. So these are 100% synthetic images of faces of celebrities that look 100%, well, at least for me, super real. And these are not existing people. This is the result of one of the recent papers at NVIDIA that is using this kind of approach, where you basically train a generator to deceive you as a discriminator to believe that these guys actually exist. They look super real. They look super celebrity. Like, I would probably, want to date one of those girls, or you would probably want to, date one of those guys. But these are totally fake. The other applications that actually allow you to exploit this great invention is arithmetic in the space of noise. So you can actually add, images of men, or subtract images of men with glasses from men without glasses, and add a woman, and you get some sort of a woman with glasses images. This is something that is quite amazing when it comes to visual space, because you didn't actually, you were not able to do it without those approaches before. And finally, one of the most important achievements of human mankind, you can transform horses into zebras. This is not as useless as you might think, because it actually allows you to generate a lot of data in a automatic way, which is one of the solutions of the biggest problem that machine learning has, which is lack of fully labeled data. So this is a cycle gun result, and there's a lot of more if you want to check that out. Okay, so how does it all have, what does it all have to do with particle collisions? So at CERN we have this huge detector, which basically records the trajectories or what happens after the particles collide. You can think about it as a big 3D camera, basically. When the collision happens, you have a lot of pixels that are being, taken, and then you try to recreate, after you take this big 3D photo, you try to recreate what happened inside the detector. And now, what is often happening is that this detector kind of fails. There is some problem, there is some errors, there are some bugs that you need to attack, and one of the solutions right now is basically to use some physics analysis, Monte Carlo simulations, and so on and so forth. It's super slow, super complex. What we try to do is simplify it. Basically, think about it as a try to generate a 3D particle collision result using GAN. So pretend that you generate something that looks very similar to the image in the previous slide. And this is super useful for anomaly detection. So you can actually imagine that we use GAN trained on a healthy detector outputs, and then when the real collision happens, you just compare the results of this healthy generated samples with those that comes from the real data. And then you detect which parts are actually incorrect, and that's how you classify what is the problem, or you classify that as anomaly. It's inspired by the research in medical processing, but it can be easily applied in other fields as well. So we have our data set. It's not possible to basically regenerate the full 3D image of the camera right now because of the resolution of this detector space. It's 5,000 by 5,000 by 5,000, a lot of pixel values that GAN so far cannot handle very well. So we instead just generate a single particle, and then we merge single particles all together and form this spider web that you see in the top. This is actually the real data that we trained with. We use a deep convolutional GAN for that. So it's a generator part actually has a bunch of layers that are deconvolution layers. It's a reverse operation towards to the convolution, which some of you might know. And then there's a convolution layers in the discriminator itself. The results are quite impressive. So we are able to get a speed up of over 30 times with respect to the current simulation techniques with just 1 order of magnitude error, which is not as bad as it sounds. And the performance tests were actually run on CPU, so if you use GPUs, the additional improvement can go even further. And it actually scales pretty well. So in the curves and in the graph in the bottom, you actually see how it scales with the number of clusters that we generate. And it seems that it's actually the future of simulation for what it's worth. And these are the results so far. So as you see, the reconstructions are not perfect. You still see some sort of jittering happening, but it's good enough for the anomaly. So if we actually apply this model for anomaly detection purposes, it works pretty flawlessly. So it's still not perfect when it comes to just reconstruction, so pure simulation of what's happening in the detector, but it works fairly well for the application that we were aiming at, which is the anomaly detection. Okay, so the third success story, the last one I promise, and then it's going to be lunch. It's online popularity prediction. So basically, we're trying to figure out what's going to be popular in social media and internet in general. This is the problem that we're facing. We work at Tooploox with one of the biggest social media content publisher with billions of views of their content monthly. And we're trying to use visual cues, such as features in the frames, the opening frames of the video, to predict whether a video will be popular or not. We're also using some sort of text detection algorithms for that. We have new shot detections and so on and so forth. This is the work done at Tooploox. And what we found out is that the sequentiality of the opening scene, so the frames at the beginning of the video, actually give you a lot of information about what's going to happen and what's going to be popular in the future, what video is going to be popular in the future. We get inspired by recurrent convolutional neural nets. This is a method that is quite successful at tasks such as activity recognition, so taking a video of somebody's cooking scrambled eggs and then figuring out that this is a person cooking scrambled eggs, as well as image description and video description. These were the original applications of those architectures. Now what we use them for is actually to predict popularity. So we have the sequentiality of the frames that are at the beginning of the video. We input it using the recurrent neural net, and we combine it with convolutional outputs. And the output of our model is actually popularity of the frames, or popularity of the video that starts with those frames. So you have this two-dimensional vector, popular and unpopular at the end. The results that we got in terms of the Spearman correlation rank are actually 30% better than the standard, well, shallow approaches where we have this before deep learning approach such as SVM combined with the handcrafted features. And this means that basically we can start playing with that in reality. And this is what is happening actually right now. We start to deploy this as a product within the company that we work with. Qualitative results, these are the best and the worst 100 videos that our algorithm detect as popular. You see obviously a lot of food, the reason being people basically watch a lot of videos of food. And that's one of the problems that we hit in our data set, and that's also a tip for everybody that plays with the data, just be careful what you have in your data. But there's also some nudity, there's also some, I think some kittens somewhere there. On the right side you see the worst, so the videos that started with the opening frames like that, and they were not so popular, and most of them are actually politicians or people facing the camera, or well, also the colors are not irrelevant, so you see this bluish sort of cold version of the colors on the right, while the images on the left are a little bit warmer. But we didn't stop there. And this is our recent work that is going to be published at CVPR this year. We looked at the attention model. So this is a model that was originally developed for translating sentences and text basically from one language to the other. It was also used to caption the images, and you see here that this is the input of attention-based model that allows you to caption the image of a bird flying over a body of water, and it allows you to actually visualize which part of the image influences the most the textual output. You see here that when the bird comes out as a caption, the neural net or the convolutional part actually looks at the bird itself, while when you look at the water, everything around the bird is actually lightened up. And we use that for our purpose. So you can think about a bunch of frames at the beginning of a video as a sequence of visual stimuli as well. So what we used attention for is actually to weight the input of consecutive frames. Within the image itself, we looked at the responses of convolutional nets, and the output is basically the score here, which is a popularity score. Obviously, you know, cute dog, high popularity, you know, no research needed. It was also quite useful for the textual analysis. So this is the title of the video, and to actually visualize the importance or the influence of a given part of the title on the final output, on the final popularity, we used attention model as well, which is quite elegant because we use the same model for both textual and visual stimuli, which, yeah, we find quite appealing. So, are we done? Well, almost, like just a couple of slides, bear with me. Basically, this is all that we've seen so far. This is the commoditized version of computer vision applications that we've been working very, well, we've been putting a lot of hard work into making these things happen. Right now there's millions or thousands of researchers all over the world. We've been building up on the shoulders of giants of the research for the last 20 or 30 years. But it doesn't mean that we can just rest now and say, you know, everything is fine and we just follow on and just do some other things. There are still some problems that need to be solved. Philip mentioned the robotics in the previous talk, and actually, me personally, I believe this is the next challenge that we have. This is a Boston Dynamics robot failing, like completely failing at basically putting just a simple, whatever that was, a box on a shelf. It requires a lot of visual stimuli to understand where the box is, where the shelf is, what sort of height the robot should put it at, and so on and so far. Maybe they don't use deep learning, maybe they don't use that much computer vision, but still, it's the next challenge that people in computer vision and machine learning try to address. How to actually take those models and play with them in real world. And this is totally different story. Like even in the videos through OpenAI, you saw that the real world is not exactly what we can so far model perfectly. There are a lot of efforts to actually model this sort of dynamics of what's happening in real world within the virtual reality. It's not done yet for sure. So have we solved computer vision? No. The other example is how this marvelous robot developed at Berkeley is actually folding towels. So this is a video that is 50 times quicker than what actually happened. 50 times, it takes basically 25 seconds to fold a towel for this robot. It means it's 25 minutes, basically. It was 25 minutes for a robot to fold a simple towel. It's quite impressive that he didn't get too bored from doing this for 25 minutes. I would just kill myself after the first 5, probably. But this is the level at which we are currently with robotics. Like, for us, it's natural to interact with objects that are non-rigid. Things like clothes, things like rubber items. For robots, it's a totally different story because they don't have the same prior knowledge that we have as humans. And now transferring this knowledge into machine learning driven system, autonomous cars or strategic games, this is something that we haven't solved yet and something we're actively trying to solve in the machine learning and computer vision community. And the last thing is that the learning with small data sets, it's still a challenge. So why people are so excited about this adversarial training is because it allows you to actually generate much more data without the need to label it. So this zebra thing, which you saw in the previous slide, it's not only about creating a fish that looks like a zebra or a tiger that looks like an elephant. It's about generating immense amount of labeled data that allows you to actually train those models and make them very useful in the future. So this is why I believe, like, so far I still have some things to do and some work to do. But that's not only me. There's a bunch of people that, I want to also acknowledge. There's a whole team at Tooploox at Warsaw Uni, and also NVIDIA helps us with their Titan X's, and we're quite grateful for that. So yeah, I think I sped up a little bit. The reason being the fact that everybody's probably hungry already after this amazing set of talks that Dominic organized and the rest of the organizers. Thanks for that. And yeah, if you're looking for any challenges to be solved using computer vision or machine learning in general, feel free to reach out. And yeah, I'm available for questions. Thank you.
Thank you very much.